Hello, welcome to chapter 15. In this chapter, we're going to perform significance tests on data that shows a linear relationship between an explanatory and response variable. So we're going to be looking at the regression model. First off, we're going to look at this problem that compared the crying intensity of babies in the first 3 months of life, and then years down the road, they took their IQ gave them an IQ test and tried to compare their intensity of crying and their future IQ score. Now let's find the least squares regression line for this data. So take a second, pause the video, and type all of these numbers into your list 1 and list 2 on your calculator. Once you have this, you have it in your stat edit. I have L1, L2. So what I want to do is go to Stat, Calc, Linear Regression. Now there's two linear regressions, 4, and I believe it's number 8. Now number 8, see how it's A plus BX? This is typically the one that makes the most sense in AP Stats because AP Stats uses a B for a slope. It really doesn't matter as long as you can keep your variables straight. So I'll do 8, and you could type in L1, L2, but it really doesn't matter for this problem because our default is L1, L2. So I'll take this and throw it over here. All right, so to write my equation, we'll have the predicted IQ is going to be my Y value, and that's going to equal 85.4 plus B, which is 1.678 times my X variable, which is crying intensity. Now find the R value. That's right down there. That's 0.38. And the R value is, so the 0.38 tells us that there is a moderate to weak, probably weak, positive relationship between crying intensity and predicted IQ and IQ scores. Now our squared value is just that value squared, so 0.1841497.5, which is about 8. So we can say, to interpret this, we say 14.9% of the variation in IQ scores can be explained by the linear regression line with, what was my X variable here? Crying intensity. Now this is all review from chapter 3. We did all this in chapter 3, but here it is again. Now for y, I should say y hat, is equal to a plus bx. A and b are statistics. If we obtain a different sample, we'll get a different value for a and a different value for b. So our slope and y-intercept will change if we got another sample of kids. So we'll want to do some inference. To do inference, we'll have to look at conditions. Now regression has conditions that are completely different than our past conditions. The first one is familiar. repeated responses y are independent of each other. Mainly, we can't take one value and, or say one person, and check their IQ 4 times. Those would be dependent on each other. So, so we just have to make sure that each value is independent. Second, we'd want the mean response time of the straight line relationship. Um, it the mean has to have a straight relationship with x. So there is a true value for y. The mean is the true slope, the true y-intercept plus the true slope times x. Now these two are unknown parameters, and so is this, I guess, because it's mu. But they're unknown parameters, and we want to make sure that that is a linear relationship. So what we do is we check the residual plot for linearity. We also want to check the standard deviation of y, we call that sigma, and make sure it's the same for all values of x. And that sigma is unknown, so we just check the residual plot and make sure there aren't any major fans. For the fourth thing is for any fixed value of x, the response y varies according to the normal distribution. So what we have to do here is we have to make a stem plot, box plot, or histogram of the residual and check for skewness and outliers. Typically, we're just going to make a box plot and look from there. So let's check the residuals, or check the conditions for the crying intensity. So conditions, the first one, we'll have to state, assume all IQ scores are independent. Since we don't have much information, all we can do is just assume that they are. The second, number 2 and number 3 both rely on a residual plot. Now to get a residual plot, first you have to do a linear regression, like we did, and then we have to go to stat plot, turn it on. We're going to do a scatter plot like this of L1 versus the residuals. So we hit second list, go down to resid, mine is number 7, other people have different values. Now hit zoom 9, and this is going to be our residual plot. Now for a residual plot, the first thing we want to see, does the data look scattered? Is there any significant pattern? Is there a curve, or is there a linear relationship? Since the residual plot is scattered, now my computer's slowing down. Let's see if it'll speed back up. Residual plot is scattered. The original data is linear. All right, the second thing we want to look for is that sigma is the same across here. Now this value is pretty far out, but it's not a systematic change in what's going on. So so it looks like over here it's about the same distance away from our line as over here. A fan would be if there's a big standard deviation here and a very little one over here, or vice versa, small over here and big over here. But here it's fairly consistent throughout. So we can say sigma is the same throughout the residual plot. Now the next thing we need to do is look at a box plot of the residuals. So we can go up to stat, turn this on, And now we're going to look at the box plot. So let's look here. And the box plot will be of our residuals, so I need to turn this to residuals. And then I hit zoom 9. And now it looks like this. Now, this data has outliers. So data has outliers. So we don't know if how good this will be at approximating. So we have to proceed with caution. We can't quite say that that's normal because of the outlier. Now, one thing that's good to check is to see if my data point here is actually good. We always have to be suspicious of outliers, and I'm actually pretty suspicious of this point. We have a residual of negative 96. It seems pretty unlikely. So let's come up here, and I think I see it right away. Do you see how that looks like it's a mistake? 1, 4. Nobody has an IQ of 14. But 15 is across from 114. And if I hit that, I can hit zoom 9 again. Oh, we'll have to do the residuals. One variable stats, L1, L2, zoom 9. Let's see if that worked out. All right. So we want to do linear regression. That was 8, not one variable stats. Now this puts it into the linear regression. And now if I hit zoom stat, now this will be here. Now let's look at the point on the right here. That is 51. Now that one could be reasonable. So I think that one is actually true. So if we look back to here, really our graph would look more like this. But it still has an outlier, so we still proceed with caution. All right, so here's a good visual on how to think about this. If we have an x and a y and we have our line, each point is has its own normal curve. Some values could be above, some values could be below, but most of the values are right near the line. And this true line is alpha plus beta x, where alpha is the true y-intercept and beta is the true slope. Now our first point in the data was 1087. What is our predicted value for y if x is 10? So we have our equation here. Nope, not there, but there. If x is 10, we plug a 10 in for our crying intensity. So 85.4 plus 1.678 times 10, and I'll get 102.80. 102.18. Now this is below our predicted value. So to find our residual, I take our actual value minus our predicted. And so 87 minus 102.18 is negative 15.18. Now use a calculator to find the residuals for all points. And look at the residual plot and the box plot. We've already did this to check the conditions. Got ahead of myself there. Now there's something called the standard error about the least squares line, or the standard deviation of the residual. This thing estimates the true value, which is sigma. But since it's just a statistic, we use the letter S. Now our calculator does not have an easy way of computing this. Um, well, there actually is an easy way to compute it. But we'll learn that tomorrow actually. The way to do this without, we can find the sum of y minus y hat squares divided by n minus 2, and then square root it. So this is the residuals. We just add up all the residuals divided by n minus 2 and square root it. So our calculator, we can do one variable stats on the residuals. So what we do have to hit is second stat, go down to resid, which is number 7. We want to do the one variable stats of the residuals. Now that didn't work. I thought that would work. All right, let's try this. Go to L3, and now go second stat. Now hit number 7, or residuals. Now we have a full list there. And now let's do this again. One variable stats of L3. That gives us a bunch of values. Now, one thing that this gives us is the sum of x squared. Now, since x is our residuals, that's at the top, that's x minus y minus y hat. The sum of that squared will be this value. So if I wanted to find it for the previous problem, it would be 11023.388. Now we divide it by n minus 2. Our n is 38. Subtract 2 from that, and we get 36. So now we just take our value 11023.3888 divided by 36, and then square root that answer, and you get 17.5. So 17.5 is our value for S. Now what that means is a typical value will be about that far from our predicted value. So our typical value for IQ will be about 17.5 from what we predicted. Now for our regression, we use n minus 2 because that's the degree of freedom for linear regressions. So or when we're using two variables. So we already found the standard error. All right, so now we can get to the confidence interval for regression slope. Like I said, if we took many samples, we'd get many different values for slope. So we can try to estimate what the true slope is with this equation. We take our sample slope plus or minus t star times the standard error of b, which is different than the standard error of the residuals. So what we do is find our slope plus or minus t star, and we have s over the square root of x minus mean squared. So we have this value, top value is 17.5 from the previous problem. Now to find this value, what we have to do is go into our lists again, edit, go over to L4, and what this says is x minus its mean. So that's L1 minus the mean of L1, which I can get by hitting second stat, go over to math, and the mean is number 3. So I'm doing L1 minus the mean of L1. When I do that, I have a whole list of those values. So I can hit stat, one variable stats, L4, and notice how that value is 1291. Or I'll pull that over here. 1291.07895. And I want to square root that. So now what do is I take the square root of 1291.07895, get an answer, and I want 17.5 divided by that answer, which is 0.48. So 0.48 is the standard error for my slope. Now that tells me that my true slope or my slopes will typically vary by about 0.48 from my true slope. So what I want to do is I want to find a confidence interval. Right now we're going to find a 95% confidence interval. We've already checked conditions. Now let's do the calculations. It's b plus or minus t star times the standard error of b. Now b is our slope, which up here we found, oh, this one might be a little bit off. Let's remember that how I had that point that was off? Let's calculate this again. Let's go to linear regression, 8, L1, L2. So it's a little bit different. Ooh, but I'm not on the right page. Here I am. So here my slope is 1.49 plus or minus my t star for 95% confidence interval. Remember my n is n is 38. There's 38 data pieces. So so n equals 38. So now we have to look at the table. All right, so on the table I got 2.042 as my t star, and my standard error from the previous problem was 0.48 times 0.48. So 1.49 plus or minus 2.042 times 0.48 is 0.98. So 1.49 plus 0.98 is 2.47. And 1.49 minus 0.98 is 0.51. So we are 95% confident that the true slope is between 0.51 and 2.47. Now here is a Minitab printout for this. Now this value right here is the slope. The value across from the word constant is the y-intercept. This right here is going to be your x variable. These top values we don't use. We'll use these two tomorrow. But this right here is the standard error of slope. And this one is your standard deviation for your residuals, or standard error about the line. And of course, r squared is r squared. All right, here's your homework. Good luck.